Welcome to the sixth session on inner product spaces. Today we are going to define an inner product or what is meant by an inner product on a complex vector space. So there is a slight twist at one place. And after that we will try to define notions which are parallel to what you have seen about real inner product spaces. And in particular, we will also prove the Cauchy-Schwarz inequality for complex inner product space. Okay, and most of the things will be very easy. Okay, now the only thing is we will miss geometry. Okay, but on the other hand, in real inner product spaces we had already defined the geometric motivation. We had given the geometric motivation and use those motivation to define algebraically. And so today what we are going to do is we will simply use the algebraic expressions, but there may not be any geometry. But the results, whatever we proved there, something similar will also happen here. Okay, that's very interesting. Please keep noticing. Okay, let us get started. Yeah, this is me, in case you did not know. Okay, this is my channel, youtube.com/ckumarhu. This is kumaresa.zoom, gmail.com. You may download the list of videos from my channel here, or you can scan this. Okay, the list of videos will give descriptions and the links of videos and also some references for them, usually which are given here too. Okay, and the list will be periodically updated. For example, only yesterday I updated the latest list, which includes infinite series playlist. Okay, and another important thing is if you want to learn a topic, okay, then it will be in that particular order. Okay, so it will be easier for you to learn. So as I said, this is inner product spaces 6, complex inner product spaces. For once, reference is any book on linear algebra except mine, because in my book I concentrate, or rather I restrict myself only to real inner product spaces, sorry, real vector spaces. Okay, the linear algebra, a geometric approach, deals only with vector space over R, because once you have learned that vector space over C or any field is the same, okay, there is not much of a difference in the beginning. Okay, all the basic algebra will be the same. So there is okay, that's why I didn't do that. Anyway, so do that. Okay, so hereafter we are going to assume let V be a vector space over the field complex field. What does that mean? It simply means we have the usual vector addition V cross B to V, and then the scalar multiplication, which is C cross V to V. Okay, the properties are the same as you have seen in real, and all the properties will be the same, right? Okay, I'm not going to waste my time on such thing. Now, what is meant by an inner product? The inner product is a map from B cross B to V. Okay, right? Exactly like the way we define inner product on R, except only one place. Watch. Okay, for every V in V, we have inner product VV must be greater than or equal to 0, and inner product VV is 0 if and only if V is 0. Okay, this is the so-called positive definiteness. This is exactly similar to what you have seen in real inner product. The second one, remember the real inner product, we said for any V and W, this must be the same, right? So we are going to change it. Okay, yeah. How are you going to change it? For every V and W, in V, we want inner product VW. This is a complex number. This complex number should be the complex conjugate of this number. And notice that if it's a real inner product, you can still write it, because for real number, complex conjugate is the same number, right? You follow that? Inner product WV will be a real number, therefore its complex conjugate bar will be same. So BW equal WV. Are you following? Yeah. So this is the only thing this differs from. Notice that this differs from real inner product. where I would have written their inner product WB itself. Okay. And the third thing is, as usual, V1, V2, W R and V, sorry, R and V, then V1 plus V2W inner product is, this is exactly the same, V1W plus V2W. So additivity wise is the same, and similarly W1, W2 in V and V is in V, then inner product V, W1 plus W2 is also VW1 plus VW2. Okay, this is exactly the same. It's like distributive law, as I said earlier. Do you remember that? Inner product is, okay, this law you should think of as like ordinary multiplication with the distributive law. Keep that, is a mnemonic. Okay, your algebra teacher, if you say that, he or she will be angry with you. Don't say that. Okay. And fourth one is, now I have to work with the complex number. Therefore, let lambda be a complex number and V and W be in V. Then I should ask what happens to lambda VW. This should be lambda BW, right? On the other hand, this is obvious, but you should see V lambda W should be lambda bar VW. Are you following? This lambda second factor comes out with a complex conjugate. Please pay attention. Whereas in the real number, just lambda comes out. That's it. Where lambda is a real number. In fact, in this case, lambda is a complex number. If it happens to be a real number, there is no difference. They are the same. Lambda equal to lambda bar, right? But in the complex number, if lambda equal to I, then this will be minus I, right? Now notice that this V lambda W is same as lambda W V bar. But by this first condition, this is okay. One, this is, you call it A. By this is same as lambda comes out. The lambda into WV and then whole bar. Are you following? This lambda comes out, right? But you know, AB bar is A bar, B bar, right? Therefore, this is a lambda bar into WV bar. But by the second condition, this is lambda bar VW. This is by 2. This is by 4A. Yeah. So this is, okay, this is redundant. Redundant meaning not necessary. It follows from other properties, namely property 2 and property 4A implies this one. Okay, but it's good to know that. Okay, sometimes algebra teachers will say it follows, it's a redundant condition, so I do not impose, but it's always a good thing to write it so that I don't know to do that. See, when I look at V alpha W, then I know alpha bar comes out. Okay, inner product V alpha W will be alpha bar inner product VW, so that will be much easier. Okay, do you understand? So this is called a complex inner product, or sometimes Hermitian inner product. On a complex vector space, on the complex vector space. I will use the complex inner product, it will be easier because it's a complex vector space, it will be okay. In fact, I should have started with the motivation, but sometimes mind doesn't work properly, right? So I should suppose my V equal to C. Okay, this is a complex one-dimensional vector space. Right? So how do I define inner product? Let's look at in Rn. How did you define? Take two vectors x and y in Rn. Okay, take x, y in Rn. Then we define x dot y equal to summation xi yi, right? Now then we check the first condition. What is the first condition? X dot x is greater than or equal to 0, etc. Right? Now suppose I have z and w in Cn or n equal to 1, also you can take z equal to z1 to zn, w equal to w1 to wn. Okay, I want to define this complex inner product. Okay, zi wi. Let me zk wk k equal to 1 to n. I don't want to write I because since we are in a complex number, this I also has a meaning here, right? So let us use either j or k for indices. It will be easier, right? But this is a good definition, because if I take z dot z, what do I get is k equal to 1 to n zk squared. But remember, zk's are real numbers, sorry, complex numbers. Therefore zk squared need not always be greater than or equal to 0. This may not be true, right? So what do you think I should do? So obvious thing is to find this is wrong, right? So the correct definition is the following. What is the correct definition? Z dot w equal to zk wk bar k equal to 1 to n, right? Now notice that z dot z, the dot product will be zk bar, which is okay, this is greater than or equal to 0, right? And let's look at only the thing. What is lambda z dot z dot lambda w? That by definition is going to be zk lambda wk and bar k equal to 1 to n, right? That is going to be lambda bar is common in k equal to 1 to n zk wk bar, therefore it is a lambda bar into zw. Okay, the rest of things like distributive law etc are obvious. Please don't mention as a distributive law. Okay, it's like a red flag before a Spanish bull. Okay, your algebra teacher will be very angry with you. Don't say that. Okay, right. So you can verify all the rest of the conditions. Okay, this is the most important example. And second example is, remember, on M and R, okay, given two matrices A and B, we define inner product AB. I don't remember. Okay, don't hold me. It may be something like trace A star B or some such thing, or I don't remember, whatever it is. Okay, this will be what? Okay, but yeah, before going, let us go back. This one, notice that if I again write Z as Z1 to Zn, a column vector, and W also like that, this is going to be Z dot W is going to be Z star W. Where is Z star? Okay, let me go back. It's worth mentioning. So let us write Z in Cn as a column vector, Z equal to Z1 to Zn, and W equal to W1 to Wn, right? Then Z dot W, as we saw, is summation Zk Wk k equal to 1 to n, right? Wk bar, sorry. But this you can say is W star and Z. So this is a, see, this is an n cross 1 matrix. This is n cross 1 matrix. What is W star for a complex matrix? If A is a complex matrix Aij, Aij in C, then A star is, all of you know, its ijth entry is jith entry of A and take its complex conjugate. Therefore, this is nothing other than W1 bar Wn bar into Z1 to Zn. Therefore, that will be this. Are you following? Yeah, right. So notice that therefore z dot w is w star with z, therefore this is an 1 cross n matrix, n cross 1 matrix, therefore it's a 1 cross 1 matrix which is whose entries are nothing other than this. This is a 1 cross 1 matrix whose entries are, there is only one entry which is z dot w as we define. Okay, very good. Now let's come to the second example. Okay, let us recall on V equal to M and R, again we define, given two matrices A and B, inner product AB we define to be trace of, okay, B star A or some such thing. Okay, I hope I'm right, but let's not worry about all these things. Okay, right, or it may be A star B. Okay, if you want, go back to the earlier video and check it out. Right, maybe if you want I can also check it, but I don't want to waste my time. And do you remember I said why I don't want to write BT transpose A? Right, can you now any of you guess why, what I am going to do? Right, take M equal to V equal to M and C n cross n complex matrices. Let A and B are two matrices here, then inner product AB I define to be trace of B star A. What is B star? Its jkth entry is, take the kjth entry bkj and take its complex conjugate. This stands for jkth entry of the matrix B star. This is the so-called adjoint matrix or whatever you call it. Okay, and as in the M and R case, you can see inner product AB is nothing other than, okay, A jk and W jk bar j and k equal to 1 to n. Okay, and if you don't get it, just slightly change that, instead of trace B star A, change it to A star B or whatever it is. Okay, these are very trivial issues. Okay, you should feel confident, okay, that to do that. If you want, take 2 by 2 matrix and check it, you know what to do. Okay, the real my thing is not, these are not very important. Third example is, let us look at complex valued functions, continuous function f from AB to C, okay, and continuous, right? And how do I define integral A to B of f of t dt? In case you don't know, write f of t, this is a real number, therefore it has a, sorry, this is a complex number, therefore it has a real part of f of t plus I times imaginary part of f of t. So this real part of f of t, you call it u of t, and this one you call it I v of t. V of t is imaginary part of f of t. Then you define integral to be integral u of t dt a to b plus I times integral a to b v of t dt. This is how you define the integral of a complex valued function. And if f is continuous, the real and the imaginary part, they are all continuous because they are nothing other than the projection, right? Okay, from R2 to R, okay, z is x plus iy, but x plus iy is, you can think of as a ordered pair x comma y in R2, and you are projecting on the first part x to get the real, and to get the imaginary part you are projecting on the second part. You know, these are all continuous functions, etc. Okay, let's not worry about such things. Now how do I define if f and g are in V, that is continuous complex valued continuous real continuous function, then integral of g, I'm sure all of you know that now, right? F of t into g of t bar dt, that's it. Therefore, if I take integral f, okay, that will be mod f squared. right? Now f is continuous, therefore mod f t is continuous. T going to mod f t squared is continuous. These are all composite of continuous function, therefore this is continuous. It's a non-negative function, therefore this fellow integrand mod f of t whole square t going to this. Okay, this is non-negative continuous function on the interval ab. Therefore if interval ff is 0, okay, if only if interval f of mod f of t whole square dt is 0. But for any non-negative continuous function, we had already proved the integral is 0 if and only if the function is identical 0. If only if mod f t squared, the integrand is 0 for all t. But this is if only if mod f t is 0 for all t, that is same as f is 0 on AB. Okay, the rest of things are easy. So we are given 3 examples. Okay, so pause, review, proceed. Okay, so let V be a complex inner product space, right? Okay, now again for any vector V, in V I define norm of V to be, look at the inner product VV, this is greater than or equal to 0, therefore take the unique non-negative square root. Of this number, right? Okay, so what are the properties? The first property is, okay, suppose norm of V is greater than or equal to 0 and norm of V is 0 if only if V is 0. Is this clear? This is greater than or equal to 0 is clear because it's a unique non-negative square root. And if norm of V, remember I told you whenever if you get a norm length of a vector which comes from inner product, you should always work with norm squared. Therefore norm V is 0 if only if norm V squared is 0. But norm V squared is by definition inner product V is 0. But since this is an inner product, that means if only V is 0. So we have proved it. Yeah. Now suppose lambda is a complex number, then I want to know what is lambda V. But this is by definition, so let us, okay, this is by definition lambda V and take its square root, right? Now use the last property when the lambda in the first argument comes as lambda V and this comes out, second part comes out lambda bar inner product VV, therefore it is mod lambda squared into norm V squared. Let us do that. Yeah, therefore this is nothing other than mod lambda into norm B. No, why I have to take mod lambda? Why cannot take this? Because remember by our definition this is a non-negative real number, I have to take the unique non-negative square root. Therefore I should not take minus of mod lambda, I should take only mod lambda. Is this clear? Yeah. So pause, review, proceed. Now let us make a remark. See, if V is a real inner product space with a inner product, okay, then we saw this is a bilinear map of V to R. What did it mean? It said that if you fix y naught, the map x going to inner product x y naught is a linear, and if I fix x naught, then the map y going to x naught y is a linear. From where to where? from V to R, right? But if it is a complex, okay, if I fix, okay, V naught in V, then W going to V naught W is not linear over C. Why? Because, so let us look at what happens to W1 plus W2. That will go to V naught W1 plus W2, that is V naught W1 plus V naught W2. So it is additive, right? But where does lambda W go to? That goes to V naught lambda W, but that is lambda bar V naught W, right? If you think of this as a map F, then F of lambda W is lambda bar of F of W. Therefore, it's not linear. Okay, it does not respect the complex scalars. Do you follow that? But on the other hand, okay, so what you do is check, let us do that. But on the other hand, okay, fix W naught, let us look at the map V going to inner product V W naught, then this is linear from the complex vector space V to complex number C. Why? Because addition is okay. Let us look at lambda W V. Where does lambda V go to? Lambda V W naught, which is by the property, it's a lambda V W naught. Okay. Therefore, what is the conclusion? The inner product map from V cross V to C is linear in the first variable, and one usually says is conjugate linear in the second variable. What do I mean by conjugate linear? Okay, if I multiply by complex number lambda, lambda comes out not as lambda but as lambda bar. Okay, pay attention, learn this, spend some time. Okay, right. So now that you have learned all these things, next question is Cauchy-Schwarz inequality true? So V complex inner product space. Notice that we are not assumed so far V has to be finite dimensional. Okay, right. Keep that in mind. It's a complex inner product space, right? So what should it mean? That should mean inner product VW for every V and W in V. This should be less than or equal to norm V, norm W. This is what we are asking, right? This is similar to the Cauchy-Schwarz inequality we have done in the real case. Now notice that inner product V W, okay, is a complex number, and again, as I said, I have norm here. The norm comes from inner product, therefore it's better to prove square version. Remember again, I already used it. If A and B are non-negative, then A is less than or equal to B, if only if A squared is less than or equal to B squared. Why? Because B squared minus A squared equal to B minus A into B plus A. This is always positive, and therefore this is positive if only if this is also positive. That means B is greater than or equal to A. Okay. Usually you see that in the last time when I used, I didn't explain that, but it's always when I say that, this proof goes in my mind. Okay, these kind of small things we keep on using so that you'll feel comfortable. So now therefore, what do you think? This suggests I should not worry about this. I should try to prove lambda VW squared is less than or equal to norm V squared into norm W squared. This is what I want to prove. Right? Now for a complex number z, okay, what is mod z squared? How many of you remember that? Instead of x squared plus y squared, there is a very beautiful thing which involves complex numbers. Themselves it is z times z bar. Yeah, that is see, remember, whenever you say mod z squared, most of the time students will say x squared plus y squared, where z equal to x plus iy. But the better way to deal with complex numbers and the absolute value will be again square of the absolute value and use of thing mod z squared is z and z bar. These are the small tricks you have to learn. Okay, therefore this fellow is therefore inner product BW and inner product BW bar is it less than or equal to norm B squared plus norm W squared. Is that all right? Okay, now go back. So how did we use that? So remember in the very first lecture, again in the last lecture when I proved Cauchy-Schwarz inequality, I mentioned an important trick. Okay, if I know addition, if I know how to square, then if I want to multiply 2, what do I have to do? I take addition x plus y and square it, and x minus y, square it and do something. Do you remember? So, and since it's linear, we also have to do something more. So in the real case, real inner product space, what did we do was we took v plus tw, where t is real and this is greater than or equal to 0. Then we made a smart choice of t. Okay, you see, this is how you should always go through the proof, so that you will see life is easy. Later you don't have to remember, it is part of you, the way multiplication tables are part of you. Okay, right. So what should I consider now? V plus, but see, now I am in a complex vector space. So what should I do? Should I take with the real scalar? No, I should stay with this complex scalar. So let lambda be some complex scalar, lambda w, v plus lambda w. So this is greater than or equal to 0. Alright, now let us do that. Now let us expand. Now I am sure all of you know, but there is a slight twist. Remember, this is like v plus lambda w times v plus lambda w. Therefore v into v, that is v squared, that is inner product vv, plus next is v and distributive, right, lambda w. I am just going slow so that you will know that. Next one will be lambda w, this, therefore it's inner product lambda w v. The last one is lambda w lambda w. So far it's okay, like our distributive law kind of thing. But this is a complex inner product. This lambda will come out as a bar. And this lambda will come out, and this lambda will come out as it is, whereas this lambda will come out lambda bar ww. Therefore I got norm v squared plus this plus mod lambda squared into norm w squared. Right? There what did you do? We chose t smartly in the real inner product case. Here what should I do? I have to choose lambda carefully. But notice that something very interesting. Remember what did I say? When I wanted to look at this side, I am writing as BW, inner product BW with its complex conjugate. Right, now let us look at this. I have lambda bar BW, this is WB, this is already complex conjugate of this fellow. And you see that this fellow and this fellow are complex conjugate of this. Right? So what do I want? I want a complex conjugate. Therefore what should I do is I choose my lambda to be complex conjugate of this, that is BW bar. But as again I did, what do I want? What I want is with a minus by norm W squared. Recall in real IPS we took t equal to minus inner product xy by norm y squared. Right? Here we are taking a bar. Why? Because of this. Do you see that? Therefore what do I get? So this is where the board will help me so that I can keep the whole thing in my front. This is lambda, but lambda is minus BW bar, therefore it is modulus of inner product BW bar squared with a negative sign by norm squared. Right? And this fellow is what? this is lambda. Okay, yeah. So lambda equal to, I want a bar. Okay, lambda bar. Okay, so let us look at this. Sorry, lambda equal to VW itself. Why? Because I want a lambda bar. Lambda bar will be VW bar by norm W squared into VW. Just go through this. I want a lambda bar. Therefore, I don't want bar here. It's just V naught part VW. Is that okay? Yeah. And what is the next one? There is a minus sign though. Therefore, next one is just lambda. Therefore, it's VW by norm W squared. But then WV inner part W is VW bar. That is the second property, right? And then plus mod lambda squared. That also will write. This is mod lambda squared. What is that lambda? This is mod lambda squared is modulus VW whole squared by norm W to the power 4 into norm W squared. Right? Do you remember in the real non part space I made a small mistake there? Yeah. Right. Therefore this cancels with a 2. Therefore I multiply everything by norm W squared. As usual, again we are assuming W is not equal to 0. Because if W is 0, the result is obvious. Right? Okay. Therefore this is norm V squared into norm W squared minus, okay, this is twice mod VW whole squared, yeah, plus VW whole squared. There, this is greater than or equal to 0. Therefore, what do I get? Norm V squared and norm W squared minus modulus inner product VW whole squared is greater than or equal to 0. Therefore, modulus of norm VW is less than or equal to norm V into norm W. Okay, pause, review, proceed. You see that the proof is exactly similar to the real case. Whereas in real case, you should notice that I tried to also just show how to get a t, because then I used a quadratic polynomial, right? A polynomial in t, second degree polynomial in t. Therefore, I used calculus to find out the minimum. Right here, what did I do? I purely went algebraically. How did I do that? Please go through this kind of, this is how you should analyze the proof, right? I wrote this fellow as this one. Okay, that helped me there. What I got here lambda bar into this, here lambda into W, but this fellow is nothing other than VW bar, right? So therefore this term and this term are conjugates of each other. Okay, therefore, but I want modulus of VW whole squared. Therefore I can choose this to be essentially lambda to be inner product BW, but I wanted to can get this thing norm W squared, therefore I divided. Okay, you understand? Please understand. See, line by line checking is easy, but next time you should learn so that you close this, try to do on your own, you will appreciate. You will never ever forget this kind of proof. Okay, and again equality case. Okay, this exercise exactly similar to the way we did for RN or real non products case. Okay, are you happy? Okay, from analysis point of view, there is an important thing you should notice. Suppose let us look at Cn. Okay, let us say alpha equal to alpha 1 to alpha n and beta equal to beta 1 to beta n. Okay, no. First thing you should notice is, notice that norm of alpha is summation mod alpha j squared j equal to 1 to n, but this is same as, okay, let me denote a vector v which is mod alpha 1 mod alpha n, then this is same as norm of v. Do you understand that? That's very crucial. Yeah, right. Therefore, let us apply this to this. Okay, you will find something very interesting. So, what did Cauchy-Schwarz inequality say? It said inner product of alpha with V is less than or equal to norm of alpha into norm of V. Yes, so norm of alpha and norm of beta. But this is same as norm of V into norm of W, where W is of course mod beta 1 mod beta n. Right? This is the modulus. Remember, this is a complex number, therefore I cannot write less than I could. I would be careful, right? I should write with the modulus. Very good. Right? Now let us look at what is the inner product of V W. This is by definition mod alpha j into mod beta j. Beta j bar, but it's a real number. Therefore, this is less than or equal to norm of alpha into norm of beta. Okay. So what does it say? This is a very crucial thing. Therefore, for any complex numbers alpha 1 to alpha n and beta equal to beta 1 to beta n, what we have is this inequality. Mod alpha j into mod beta j is less than or equal to summation alpha j squared into summation mod beta j whole squared to the power half j equal to 1 to n. Okay. So this inequality will be very much needed, especially if you do an analysis, partial differential equations and functional analysis, Hilbert space, etc. So learn this well. So you don't simply remember this kind of proof, okay, this statement, but if we are given as some ordered n tuple of complex numbers, I have something much. See, this one will only say, see earlier if I use alpha, okay, simply the inner product alpha beta will be summation alpha j beta j bar. Therefore, modulus of inner product alpha beta will be less than or equal to norm of alpha into norm of beta, right? But this means modulus of modulus of alpha j beta j bar. This is less than or equal to summation alpha mod alpha j squared power half into summation beta mod squared to the power half, etc. But notice that we have proved a stronger inequality. Okay, this inequality, okay, is stronger than this inequality. This stands for stronger, not greater than. Are you following? Because notice why? Because this is algebra, but I cannot stop doing analysis also. This is less than or equal to, okay, modulus of alpha j into beta j, but this is equal to mod alpha j into mod beta j. You understand? This fellow is less than or equal to this, cannot guarantee something bigger. Are you following this? Okay, alright. If I say 4 is less than or equal to 4 and a half, but if I say 4 is less than or equal to 5, I cannot say less than or equal to 4 and a half. You understand? But what we are saying is something bigger is also greater less than or equal to whatever we have. Okay. So pay attention. This kind of subtleties you should learn. These are the things which teachers do not want to push you. They just want it streamlined, class notes, very easy. Okay. But when you are facing some kind of competitive exams and interviews or research, you do not know how to think. These are the things which will help you. Are you following? Very good. So the last thing, right? Now, given two vectors, let this be a complex inner product space. Okay. Take two vectors in V and W. I say V is orthogonal to W if inner product VW is 0. You see that? Now there is absolutely no geometry here. I simply say that's why I didn't want to use perpendicular now. We chose a slightly Latin word, orthogonal. Okay. Whereas in the case of real inner product space, we have the formula. See, VW is nothing other than norm V, norm W into cos theta for V and W not equal to 0. Right? Therefore, when theta equal to pi by 2, then this is going to be 0, and if this is 0, if only theta is pi by 2. So it made sense. But there is no such formula. Why there is no such formula? Let us look at. Because inner product VW by norm V into norm W, okay, this will be a complex number. And where does it lie? It lies in the set of complex numbers Z in C such that mod Z is less than or equal to 1. That's it. Whereas in the earlier case, real inner product space, it's a real number. It lies in the interval, closed interval -1 to +1. Therefore, using the property of monotonicity of cos, bijective property, cos maps 0 to pi onto the interval -1 to +1. But it decreases. So it goes from 1 to -1 monotonically decreasing. You use that fact to define cos theta. Here I can't do that. But what do? This is what mathematicians do, right? You have something which intuition, you bring it to some equivalent form which is purely algebraic formal, and use that formal thing to explain, to define more abstract thing. Is it difficult? It's not difficult. That's how you define group theory, right? Groups, how did you define? Okay, all such things. Okay, and if you are learning topology, metric space, you do that. Distance between two real numbers you learn, then you want distance between 2 points, you abstract it. All right, learn this is abstraction. Okay, so now before I will end up with the interesting thing, therefore let us be, okay, we will do, okay, even in a complex inner product space, this is our definition. The time is up, so let me start. Now I claim V plus W squared is norm V squared plus norm W squared. This is our Pythagoras theorem. Why? This is V plus W, but this is BV WW plus VW plus WV, right? But this means VW is 0, therefore the WV is also 0. Therefore this is 0, this is 0, therefore I get norm V squared plus norm W squared. You see that? So it seems to be a good definition. Even though I cannot define angle, I can define orthogonality in complex inner product spaces, right? One specific angle I can define, namely they are perpendicular to each other. Do you appreciate that? Yeah, isn't it great? I cannot define an angle, notion of angle between any two vectors in a complex inner product space. But what I can do is I can define when they are perpendicular. And it's a very nice definition because Pythagoras theorem is true. Because if I have V and W, what is V plus W? That is the diagonal. Okay, this is V, this is W, right? You get a rectangular square, then you take the diagonal, and that's a Pythagoras theorem. I hope you follow that, right? That's how we found out the length of between any 2 points x1, y1, x2, y2 and R2 using Pythagoras theorem, right? It's very beautiful. Okay, we will continue our study. Okay, I hope all of you enjoyed. Take care, stay safe.